Hi everyone, Mr. Markwick here. Today's video is an introduction to discrete models. In particular, today we're going to be looking at critical path analysis. In order to do that, we're going to be looking at precedence tables, precedence networks, in order to complete or to determine the minimum completion time for a project. Now, a project, we say, is made up of a number of individual tasks. And you can see that the project that they've given us to start with here is making a cup of tea, which is made up of 7 separate individual tasks. And there is a time associated with each of those tasks. So what we want to work out is what is the minimum completion time for making a cup of tea based on the information we have here, of course. So what we need to do is, first of all, create a precedence table, okay, which I guess identifies which tasks are independent, don't require tasks to happen beforehand before we can start them, and tasks that are dependent on other tasks that have already happened. So looking at the list of 7 tasks here, which ones are independent, have no prerequisites. So retrieving the cups from the cupboard is an independent task because we don't need to do anything before we retrieve the cups. But placing tea bags into the cups is dependent on us retrieving those cups from the cupboard already. Okay, so a prerequisite of task B is completing task A first. Task C is filling the kettle with water. Again, that one's independent because we don't need to complete any tasks beforehand. But task D, boiling the water in the kettle, requires us obviously to have water in the kettle first. So C is a prerequisite of task D. You'll go on and see obviously task E, F, and G are also dependent on other tasks happening previously. So those are my 2 independent tasks, or tasks that require no prerequisites. So what we do is we then fill in a precedence table based on that information. Here it is here. Tasks A and C, as you can see, have no prerequisites. Task B can only be completed when task A is done. So we say A is a prerequisite of B. Task D can only be completed when task C is done. So we say C is a prerequisite of task D, etc. So what we're going to do now is we're going to draw a precedence network in order to work out the minimum completion time for this project, making a cup of tea. I've got some dot points here to help us out with that precedence network. Basically, a network is obviously made up of nodes and edges, or nodes and arcs. In this case, we're going to use arcs, which is basically just an edge with an arrow to show the direction of that task to the end of that task and the start of the new task. So nodes will represent the start and or finish of a task, starting with our starting node. And from our starting node, first of all, we need to identify tasks that have no prerequisites. We've done that here. It's task A and task C. They have no prerequisites. So tasks with no prerequisites are attached to the starting node. All right, so we just put an arc from the starting node with task A and task C. It is as simple as that. Then it gets a little bit more challenging. So any tasks with a prerequisite should be directly attached at a node where any prerequisite tasks meet. So task B has a prerequisite of task A, so it should be attached to a node where the prerequisite task A is attached. So B backs on to task A. Task D, I'm moving down the table here because we've already done C obviously, has a prerequisite of task C, so it'll be attached to a node where task C meets, so that's my task D there. Then we move on to task E, but this is a little bit more confusing because it actually has 2 prerequisites, task B and task D. So what we actually need to do is we need to erase one of those lines so that both of those arcs meet at the same node. So I'm going to remove, because that's a little bit close to my writing, I'm going to remove task B and redraw that arc for task B where it meets at the same node for the completion of task D. So B and D both finish at this node, which means I can then start task E from that node. Okay. F has a prerequisite of just E, so F will then follow on from the completion of task E, and G has a prerequisite of F, so it will flow on from the completion of task F, which takes us to our finish, which is the completion of the project, or the cup of tea is ready to drink. Now, that is the precedence network, okay? But what we're going to do is use this precedence network to work out the minimum completion time for this project. So what we're going to do for each task is I'm going to attach the time to each of those arcs. So, for example, retrieving the cups from the cupboard takes 15 seconds. So I'm going to weight this arc with 15 seconds. For task B, it was 10 seconds. Task C was 20 seconds. D was 100 seconds. E was 10. D was 15. And G was 10 as well. So based on that, we have to work out the minimum completion time. Now, the shortest path through this precedence network is to go A, B, E, F, G from start to finish, obviously. But if I followed that path from A to B to start task E, which was pouring the boiling water into the cups, the water actually wouldn't be boiled yet, okay? Because 15 plus 10 is 25 seconds. But keep in mind, task C and task D also need to be complete before I can start task E. So at this point here, at this node here, the water's not actually boiled. So I can't then pour that into the cup. So what I'm actually looking for is taking the longest path, which will tell me the minimum completion time. I know it sounds a little bit counterintuitive. I want to find the longest path through for the minimum completion time, but hopefully that explanation makes sense in terms of these tasks, C and D, need to be finished before we can start task E. And in order to do that, we can't start task E after just 25 seconds. So I'm looking for the longest path through, which would obviously be C to D to E to F to G. Now, if I add all those times together, it gives me a minimum completion time of 155 seconds for this project, which is obviously making a cup of tea. Now, what we also want to identify is the critical path, the path we just followed to add up all those times to give me that minimum completion time, which is along path C, D, excuse me, E, again, F, and G. So that is my critical path. So the critical path is important because obviously it tells us the path we've taken to get the minimum completion time, but also identifies all of the critical tasks. So tasks C, D, E, F, and G are real critical tasks. Obviously A and B are critical as well, but what we mean by critical tasks is any delay in one of these tasks will increase our minimum completion time. For example, if it takes an extra 10 seconds for task C, which is filling the kettle with water, then my minimum completion time is going to increase by another 10 seconds as well. So important to understand that any delay or increase in time in one of those critical tasks which appear along the critical path will increase my minimum completion time. One thing I do want to point out here as well, that when we looked at this precedence table here, it says that notice A is a prerequisite of B. We've already sort of discussed that. And B is a prerequisite of E. So A is also a prerequisite of E. But A is not listed as a prerequisite of E here because we only have to list the immediate prerequisites of a task. And because B has the prerequisite of A, it's implied that A is also a prerequisite of E. Okay? A little bit confusing, but let's look at another example and try and break that down a little bit more. This example involves making a pizza, and this time there are only 5 tasks to complete this project. Again, each task has a time, in this case in minutes. So which task can be performed independently? Okay, so no prerequisites. So we're looking at the tasks that don't require any task to happen beforehand. So defrosting the pizza base can happen independently. So task A. Preparing the toppings, that can happen independently. So task B. Placing the sauce and toppings on the pizza, well, we can't do that until we've done task B. Heating the oven, well, that can happen independently. We don't need to complete anything before that. And then cooking the pizza, well, we need to make sure that everything is done before we can cook the pizzas. So that is dependent on other tasks happening beforehand. Next question says, which tasks are prerequisite tasks? Not which tasks have prerequisites, which tasks are prerequisite tasks, okay? So task A, B, C, and D will all in some way be prerequisites because we can't do one until we've done the other. So we can't, for example, we can't prepare the toppings. We can't place the toppings and sauce on the pizza until we've prepared the toppings. So we say that C has a prerequisite. In fact, I should write B is a prerequisite of C, just because the way the question is worded. So B is a prerequisite of C, but also for cooking the pizza, A, B, C, and D are all prerequisites of cooking the pizza. But again, because B is a prerequisite of C, we don't really have to list B again because it's implied that in order to do task C, which is a prerequisite of E, it's not an immediate prerequisite. So prerequisites for cooking the pizza are A, C, and D. So A, C, and D are prerequisites of E. Okay, again, notice there that I didn't list B again here. So then construct a precedence table for the project. Now we have the time. So task A is 5 minutes. It has no prerequisite. Again, we mentioned that there. Task B takes 6 minutes. It has no prerequisites. Preparing the toppings. And task D, which also has no prerequisites, takes 8 minutes, heating up that oven. Now task C, which is placing those toppings on the pizza, takes 4 minutes, but its prerequisite is C. And task E, which is cooking the pizzas, takes 22 minutes, and it has prerequisites I put C down here. C is a prerequisite of C. B is a prerequisite of C. A, C, and D are prerequisites of task E. So based on that, now we can draw our prerequisite table, starting with our starting node. And from our start node, we'll have the tasks that have no prerequisites. So in this case, it's A, B, and D, heating up the oven. From there, I'll then look at adding on task B to, adding task C onto task B. So when task B is finished, when we've prepared the toppings, then we can start task C, putting them on the pizza. And then task E is our last task. We've already got 4 tasks here indicated by those 4 arcs. We're doing a arc for task E, but it needs to meet at the end of task A, C, and D. So what I need to do is then extend these arcs, A and D in this case. You can draw these arcs, these networks however really you want. But I'm just going to rub those out there and then just draw those arcs to finish there at the same node that task C is finished. So then we can start task E, which is actually cooking those pizzas to finish that project. Again, we're looking for the critical path and minimum completion time. So before we do that, we need to pop in the times for each task. So A takes 5 minutes, B takes 6 minutes, C takes 4 minutes, D takes 8 minutes, and E takes 22 minutes. So again, we're looking for the longest path. Obviously, A, D, and B, C will take us all to this node here. So we're basically looking for the longest path to get to that point. So it can either be 5 minutes, 8 minutes along arc D, or 6 plus 4 minutes, which is 10. So 10 is the longest path to take us to that, plus 22, 32 minutes. So the minimum completion time is 32 minutes, which takes us along the critical path B, C, E. All right, so critical path is B, C, E. Again, critical tasks are tasks B, C, and E. I know every task there is critical in terms of completing this project, but these are the ones that fall on that critical path, which means any delay or increase in time for one of those 3 tasks will increase the minimum completion time. Okay, so that's it. Let's look at one more example. If that's enough for you, that's fantastic. You can switch off now, but I'm going to go through one more example here when we've got just a prerequisite table. It doesn't tell us what the project or the tasks are. It's just got the tasks, a duration or time, and the prerequisites listed. So again, first thing when you draw your precedence network is the starting node, identifying the tasks that don't have any prerequisites. In this case, it's task A and B, and then attaching those tasks without any prerequisites to the starting node. So A and B are attached to my starting node. Now, the next step is to attach the tasks that do have prerequisites to the node where those prerequisite tasks are immediately attached as well. So for example, task C needs to be attached to the node where task B finishes. So task C will start here. Task D also has a prerequisite of B, so we can also attach task D here. But task E has prerequisites A and C. So what I'm going to do is I'm going to just rub out this arc for task A and join it here so that it finishes at the same node that task C finishes at. So A and C finish at the same point, which means we can start task E. And task F has prerequisites D and E. So these 2 arcs, D and E, also need to be at the same point. So let's rub out arc for task D and redraw that in so it finishes at the same point task E does, so that we can start task F. So that's task D, and that's the end or the finish of our project. Again, what's the minimum completion time? Well, let's weight those arcs with the times. So A is 4, B is 3, C is 3, D is 2, E is 4, and F is 1. Now, this is a little bit more confusing to work through, but again, we're looking for the longest path through to the finish. So to get to this point, there are multiple ways we can go. We can go from the start along task A, 4 minutes, plus 4 minutes. So there's possibly 8 minutes to take us there. Or we can go 3 plus 3 plus 4, which is obviously 10. All right, we'll use minutes in this case. Or we could go 3 plus 2, which is 5. Now, obviously, we want to take the longest path there, so which is 10. So I can remove the 8 and the 5. And from that node there to the finish, we're adding on an extra 1 minute. So 11. So the minimum completion time in this project is 11 minutes. I just made up minutes. Sorry, I didn't actually say minutes there for duration. But let's just go with that, which means the critical path is along the path B, C, E, F to give us that minimum completion time of 11 minutes. So critical path is B, C, E, F, which means B, C, E, F are also all critical tasks, and any delay in one of those tasks will also increase the minimum completion time. Now, what about if we increase something like task A, the amount of time task A? How does that impact the minimum completion time? Well, it might not necessarily. If it increased by, say, for example, 1 minute, it wouldn't increase the minimum completion time. But if it increased by 3 minutes, then actually, if I cross that out and put 3, so add 3, so make it 7 minutes, then you can see that 7 plus 4 is greater than 10, it's 11. So it's going to increase my minimum completion time if it becomes the new critical path, okay? So that's important to understand as well. Anyway, I'll end it there. Hopefully that helps. My next video, we're going to be looking at, I haven't looked at in this video at dummy links, so I'm going to be looking at that in the next video. But yeah, basic introduction to critical path analysis and discrete models by looking at those precedence networks and precedence tables in order to work out minimum completion time and critical path.